Welcome back, everybody. I want to first just remind us we do have an EM assignment coming up. Per usual, I'm going to give you an extension, so give you a little bit more time to think about it. I don't think it's an overwhelming activity. I think the Bayes bootstrap delta does take a lot of time, sorting through a lot of different situations. Probably in hindsight, it doesn't take too much time. But I think the first time through that exercise does take time organizing everything. And then you get down, I need to compare everything, so I need to put everything in the plots and get all that manicured. And if you guys are like me, it's like you can code something up pretty quickly and get the basic idea, oh, it seems to work, but polishing it all and getting your figures and writing it up takes a ton of time. So anyway, I did scan through all those assignments. I think they look pretty good. If you put in a reasonable effort, it's going to count fully. So if it looks like you didn't answer or address the questions or make a comparison, that'll count more towards when I'm making decisions on where you're at on the boundary of grades. So I'm going to look at your effort there. So, but if you've turned it in, check. And then if you've done a really good job, I'll use that to catapult you over. Same thing on the EM assignment. I don't think there's as many opportunities, but let's just kind of glance at it real quickly. Somebody mind on the lights? So just real quickly, this is on the website. So the EM assignment, so we're studying mixture models. We've written that down quite a few times. Okay. So mixture model, if you can't see that, that's a normal distribution in multivariate form. And it says basically, here's the algorithm for updating everything. You're going to update the probabilities, you're going to update the means, you're going to update the covariances. If you want to update the pi-k's themselves, you can, but you don't actually use those things for anything in the algorithm unless you've chosen to use those as your prior. So for me, I would probably, just because I'm inclined to think about the full uncertainty of everything, and I don't like double dipping my data and things like that, I'd probably use the uniform prior, or if I had some subjective weighting that I knew that I expected there to be an imbalance in the group sizes, then I could encode that through a prior. You could also use the pi-k's themselves, and it's very, very similar to using the uniform prior. The uniform prior, I would say, is biased in the sense of making everything uniformized. Anyway, if we ended up using the pi-k's, you would have to compute them as well. So I'd encourage you to try out a couple things, compare and explain the differences in what you observe. That's science. So pick things, compare for reasonable reasons, see what's different, and see if you can explain it. So basically the algorithm is just updating these formulas over and over and over again. I'll give you a simpler version and run a simulation for us right now, and you'll do a more complicated version. Part A and B says just derive these formulas, the MLEs. So these are the MLEs that we computed. So over on the left-hand side, there's an equal sign right here. Here's just your updating formulas. And those are the MLEs. So they're just the weighted averages. So very similar to your empirical forms for computing variances in means, except they're just weighted averages with the probabilities of each individual data point in the set. And so you're weighting using that weighted average form. So you're just going to derive these. So all you have to do is just take the log likelihood of this mixture formula right here. We've written that all out, exactly what that log likelihood looks like. So that was the thing after we took the E step in form Q. We have that. You're going to take derivatives over mu and sigma inverse, set it equal to 0 and solve. And you'll get these back. So first part is just a basic sort of Sellenberger exercise. Maximize something, you know what the answer is already, and derive these. And then part C is do a simulation study. So that what I mean by that is pick some different configurations, some mu's, some sigmas. So different dimensionality, at least 2-dimensional or 3-dimensional, at least. So different variations in sample size. and throw out some different configurations and show how the algorithm converges. So if you want to ask me which mean do I pick, and which dimensionality do I pick, and which covariance matrix do I pick, I'd say pick a bunch. Pick a few. So if you can't think your way through like scaling it up, and if you thought 3 dimensions was a good thing to look at, maybe 4 dimensions is also a good thing to look at. So I'd probably do cases, how does it work in 1D? How does it work in 3D? How does it work in like 10D? Or something like that. I'd be pretty satisfied with that. Which are the mu's and the variances? Pick some means that are well separated with respect to the variances. Pick some means that are close to each other with respect to the variances. And so as we move the modes closer and closer to each other, the algorithm struggles, as you would expect. As we crank up the dimensionality of the problem and don't have as much data, the algorithm struggles. As you increase sample size, the algorithm gets a little bit better. So just show those basic behaviors. Sound good? I'm sure you can be creative and pick some different means and variances. You're allowed to make choices. That's what part C says. So not a lot to read through on this one. Let's just look at an example. I coded this up in 1D, and I've done this just with the means. And I've done this just again in 1D, so your code will be a little bit more involved than this code. But let's just look at what this code does. I picked some means. I could have picked these in functional input values, but I just hard coded it in here. So I picked some probabilities. I'm going to do this just a 2 mixture model. So 2 modes is all my code does. You'll have a few more modes than just 2. So you can probably let that be a parameter in your code if you want. If you want to hard code it in there, that's fine with me too. I have n for sample size, and I have some variances. So I'm not going to update the variances in mine. I did this really simply, so this is just a simpler version of your code. My variances are the same in both my modes. So they're variance 1. Yours are going to be different, and they should scale up to covariance matrices as well. So high dimensional forms. So the first step is I simulate the data. So here's just a 2-component mixture model, so I'm just flipping a coin, which mixture component I'm in. So this is really just a Bernoulli coin flip. Yours is going to be multivariate form of it. So the multinomial distribution. You'll do a coin flip, pick which mode you're in. The only thing that I'm changing is the mu's right here, and they're hard-coded up here. So I pick just randomly 11 and 2. Those are good values. These are well separated with respect to this variance being 1. So simulate the data, I collect it all up. Then the EM stuff is down here. So I usually plot everything just so you can see it, see what the data looks like. And then I'm just going to run EM, and EM is just this loop down here. So in this loop, what do? I update the P's. And I do it just like those formulas. So all I'm doing is I'm taking the normal form, and I'm just plugging in the current value of my parameters, whatever my current mu's are, right here for the different mixture components, multiplying by whatever my prior was on everything. So I've cheated in this. I get to know what the pi's are. So I know what the pi's are. I'm not updating them, so I just pick what it actually is. So that's fully cheating in a real example. But again, a simulation study, what I think you should do when people come back and they say, I've got these 20 things I'm trying to update in my model, and I don't know where the error is. It doesn't work. So how do you debug it? You go and you take 19 things and you fix them. And you know what their values are. You don't try to update them, and you make sure the one thing you're updating is working well. Make sure that thing converges. And then you start opening up some of those other things that you don't know, but you don't do it all at once. You do one thing at a time. So this might be a precursor in how you debug everything. See if the means update correctly and then scale it up. When I try to code up 2 or 3 ideas simultaneously, and I go to see if it all works, guaranteed failure. So I've learned over the years, I just update one thing at a time, and then I move on to the next thing. Make sure things work in sequence. I don't know if you guys write your code and just hope everything works, hit go, and then you, I'm gonna guess, always get the same result. Doesn't work. Kristen?
I'm a little confused on updating the keys because shouldn't we be plugging in data instead of, oh, I see the Y.
The Y's in there.
What are the mute? Should we not know what the mutes are?
They get updated, that's the theta t minus 1.
Okay.
So I'm using I have to have some zeroth value. So I've got my initialization of everything. So how did I initialize everything? I picked random. So I just randomly pick things. So that's also a good idea. Sometimes you want to start everything at the truth, make sure it stays there. But this is the one part that I'm not really cheating on, is I'm letting everything just update in the worst possible. Like my initialization is not smart at all. So later on, if I were trying to build like an industrial version of this, I'd work on something that had smarter initialization values. So one possible algorithm I could use to initialize is k-means or something like that. Might use k-means and use the Hallonovus distance instead of actually the arithmetic mean. And that would make things a little bit more akin to this model. Since the variances are the same in this code, k-means would work just fine. So just things to make connections with. So yeah, you've got a current value of mu, and I check to see how close that y is to mu relative to v. So that's how we're updating the probabilities. I normalize them, so just basic averaging. So I could compute these pi k's and just take the mean of those. I guess that's what I've actually done. Oh, I take it back. So this code actually uses that version of I'm using these PKs and plugging them here, so I guess that's my notation. So I'm doing that sort of reinforcement learning version of these. It's a violation of the likelihood principle because I'm maximizing everything works great. So if I were trying to learn the uncertainty intervals and everything, I think we would make them too narrow. Make your scientists happy, oh great, I love narrow intervals, and then they're shocked when something's outside of them. So we can never learn this lesson correctly, it seems like. So, and then I update the mu's. So I just have this in a loop of two things. I could have hard-coded that into two different lines, but if you wanted to adapt this code higher values of k, you could just input a cap k right in there. So, and I update the mu's accordingly, and they're just those weighted averages. And that's all we do. And I'll print out some values for you, so let's just see how this thing runs. EM example, there's my data, pretty well separated. This algorithm should work. And here's my iterations flying by, and we can see what it's converging to. The mu's are 2 and 11, and the p's are roughly what I initialized them out. The original p was 0.3. So, and that's my answer, so it's converged really well. So you should get something like that. If I ended up pushing those modes closer together, it probably won't converge quite as well. We can explore that real quickly. Let's just run it one more time. So it seems to work again. I simulated new data when this happened. So it's not the same data set. If it was the same data set with the same random seed, it should run exactly the same. But this is a little bit different. So 0.3 and 0.7 again, 2 and 11. So we have some values again. This is switched now. This is 0.7 and 0.3, and the modes have switched. So I just want you to be aware of this phenomena. This is label switching. It doesn't know which compartments you called mode 1 and mode 2. So this is something, it's a real issue when you're like trying to do a simulation study and see how often it classifies things correctly, is you would need to match up the modes to each other and somehow have some rule in your code to say which mode is which mode. So if you're just running a simulation study and you're saying, well, mode 1 is mu is 2 and mu is 11 in mode 2, and I was comparing that in my code and it was switching, then I might get this really weird contorted MSE value that the code's actually running properly. So you need to do the alignment and everything and handle the switching part. I'm not asking you to do anything like that in here, but just be aware of it. So how do you switch label switching? What I usually do is I end up locking down the definitions of the modes, or I end up ordering them in some basic way, and I say I'm going to order with respect to mu's or something like that, and I have to have some rule for ordering things and just stay consistent when I'm doing comparisons. It's one of those things, when you get around to doing a full-blown simulation study, you'll go, this is a very trivial idea, but there's some implementation over it. It's kind of a pain, but you're always stuck with it. I heard somebody give a talk one time that they're like, I'll give you a theoretical way of dealing with label switching, and it's like, what? This is like kindergarten. So what do? Lock down one of the modes and start locking them down as you go, and that's usually the solution. Let's just run it one more time, just for sanity, and change the answers a little bit. If I ended up pushing these modes closer to each other, let's say that's like 3 and 2, so they're really close to each other with respect to the variance being 1. You can see how well this thing works. It's not bad. So it's actually surprisingly good. 3 and 2 were my numbers. They're a little bit off. But if I tried to eyeball that and said that's a 2-component mixture model, there might be some evidence of that visually. I can't really see it. It's not bad. That's an artifact right there, I think. Maybe not. So there's some idea that this is a bimodal distribution, but you don't really see it that well in here. But the algorithm actually works better than your algo. So here's a case where the algo does something for you. Let's run it one more time. So about 3 and 2. Of course, those aren't as precise or as close because we would need a really big N to capture this. So if you do have different variances in the model, that gives you the ability to distinguish those 2 modes a little bit better as well. So pretty cool. So you'll be coding that. Cool.
How would you get the uncertainty of your estimates?
Okay.
Not easy question.
They could be the full-blown Bayesian and put a prior on those as well and take it through MCMC and try to build up a Bayesian inference and come up with a posterior on the thetas. So you could also do some of the classical sort of stuff, and I take the MLE estimate and then I plus minus some amount of standard errors into it. So that would be kind of the classical approach that I would be like, wait a minute, it should all be done jointly, do the full Bayesian thing. So there might be some disagreement on how you handle that versus how I handle that if we're coming from different paradigms. But I would say, be the full-blown Bayesian, don't just average out the unknown thing, which is the mixture labels, and do Metropolis Hastings maybe on the thetas. So that's one solution. That would be my preferred solution, but it's a matter of taste. So for normality, there's other things you can do that would be pretty close. So if we are working on more complicated models, maybe I have an advantage, but it would depend. So with normal stuff, a lot of Bayesians and non-Bayesians tend to agree with each other. So I'm not asking for that in here, but you could do some of the stuff they teach you in other inference classes, MLE plus or minus some amount of standard errors. And that would be one solution. Cool. Let's make that due on April 26th. Is that the 26th? 25th, right? 25th is Friday. No, 26th. Yes. Due April 26th. I think we'll do a review on April 25 at 6 p.m. Yeah.
I think we also have a homework due that day too.
You do, yeah, there's some homework that's due. What are you doing? Oh, you've got your designer with your models test this Thursday, right? Okay, so no conflict there. Yeah, there's another set of homework problems, so also be chiseling away at those. So there's like 4 or 5 problems. It's not too many, so we can review those as well. I want to keep that due date at the same place. So I want you to practice problems, because that's what keeps us primed and good to go for midterms and finals. So let's just stay on the gas with problems, also be going through the chapter, looking at examples, working those problems, just to stay in practice. I think the light. Yeah. Okay. Let's do a couple last things of chapter 7. So I'm going to take the rest of today, and tomorrow maybe a touch on Friday to clear up chapter 7, and then we'll jump into hypothesis testing. So chapter 8 stuff, and I'm going to go through the Neyman Pearson lemma, tell you what they're talking about. I'm going to skip all Bayesian testing, and I'll tell you at least on the last day what Bayesians do, and I'll say there's a lot to be considered here. So take an advanced inference class if you're interested. Okay, let's go through Rao Blackwell. So this has a proof attached to it. This would be a contender for the simplest proof in the book. So super simple. I do have some questions about it. Probably the simplest proof is that invariance of the likelihood, I would say, or invariance of the MLE. So that one-liner where you're just connecting two equality statements. Okay, Rao Blackwellization. Let's just write it down. So consider some estimator. I'll call it W. And we have some property of W. Expectation of W is equal to tau theta. So this means that W is unbiased for tau theta. So it's not unbiased in theta, it's unbiased in tau theta, some function of theta. So this was the part I was talking about when I was talking about moment matching, that it gives us a little bit of freedom, that we don't have to actually match everything to the empirical moments. We can match it to functions of moments. And an example of that was when we looked at S squared being unbiased. So that was a method of moments estimator, but it was unbiased in a function of sigma squared, of sigma. So method of moments, just since we're thinking about other things that we've done, it's unbiased. The only property you could really guarantee about method of moments is unbiased in however you do the matching. So it could be unbiased for the second moments or the first moments or some functions of moments. And so let's say, okay, so I think this is all we really need. Consider this estimator. Now I'm going to end up considering a new estimator. So let T be a sufficient statistic. So we're going to form a new estimator. A new estimator can be formed as, I'll say, the expected value of W conditional on T. And I'm going to give this some name. I think the book uses VT. So this is just a new estimator right here that I can form using my old estimator and a sufficient statistic. So the presumption in this setup is that maybe doesn't involve the sufficient statistic. So an example might be you do method of moments and you match to the first moments, and those don't happen to be sufficient statistics. So I could maybe get the sufficient statistic. A minimal sufficient statistic would be even better, but it's not necessary. It just has to be some sufficient statistic. And I can condition on it, take my old estimator and build this new estimator by doing a little bit of math. So finding this expectation. So here's some facts about VT. I'm going to give this a name. I'm going to call this the Rao Blackwell estimator. I wouldn't say that this is super well accepted, this use of English. This is what I call verbing. So, and verbing is a verb itself. Verbing is a form of verbing. So, this is a new thing. We can either accept that or not. I like to call it the Rao Blackwell estimator. Okay, here's some properties. Expected value of VT, our Rao Blackwell estimator that we formed using W and T, is also unbiased for tau theta, so it has the exact same level of bias in theta that we get from the original estimator. So we don't change the bias in it. But the variance of VT is less than or equal to the variance of W. I'll just give you a heads up. If W already had the sufficient statistic in there, that's when the equality would hold. So we wouldn't get anything by doing that. So if I went to a normal distribution, I already used X bar as my statistic for estimating mu in that distribution. If I built a new estimator conditioning on X bar, the sum of the Xi's, or any form of the sufficient statistic, I would still get X bar back. It would be the same exact answer. So the presumption is that maybe I haven't used the sufficient statistic. So the only place I can really think that this is useful is in just getting us to think about you should have used the sufficient statistic in the first place. So this is kind of the statement that I was thinking about when I said, if you're not using a sufficient statistic, expect to get clobbered. And so, not necessarily in your bias, but in your variance. And I would say variance is the critical thing in statistics, understanding the uncertainty, how things move around, and quantifying that. So that's the big deal. Okay, let's look at an example, just real quickly. This is an example I've asked many times in the past. I'm not saying right now that I'm going to ask this example. I'm inclined not to, but you never know. So, here's just an example. Say that x1 to xn, I'll just put this in vector form, comes from a multivariate normal with mean mu's. And I'll say this is sigma squared times I, where I is n by n. This is exactly the same as writing this. xi is normal with mean mu and variance sigma squared. They're identical to each other. Because that has zeros and all the off diagonals, so there's no relationship between the variables. There's no covariance. Let's say I ended up just trying to estimate mu with x1. So x1 is an unbiased estimator of mu. So great estimator. No, it's horrible. So we've thrown away most of our data. This is not a great estimator. If you're interested in just explaining to somebody my bias isn't the only thing going, this might be a good example. So it's unbiased, but I can drive down my uncertainties by using all of the data. So we know the variance in this estimator is sigma squared. We also know that x bar is a sufficient statistic. It wouldn't make any difference if you sum the xi's. I'll let you convince yourself of that. Everything works out exactly the same. But let's do some Rao Blackwellization and just see what happens. So I'm going to Rao Blackwellize like this, X bar. So that's my Rao Blackwellized estimator. So this would be phi t, where that's t, and that's w. Just using the old notation. So this whole thing, I guess I already have that. So we just need to figure out what that is. Let me show you the easiest way to do this. Probably the easiest way to do this. Let me just have you remember something. So just an aside. So recall, hopefully you recall this, but if you don't, put this in your memory. If you want to derive this once or twice so you can remember it for the rest of your life, that's probably the right way to go. So let's just say I have two random variables right here. I'm going to call these, I'm going to recycle a little bit of notation on, well, let me do it like this. I'll do it more consistently with how I normally do it. So I'm going to consider just Z1 and Z2 as my random variables. I don't really care what the dimensionality of this thing is. This could be a vector, this could be a vector, that could be a scalar, that could be a scalar. So let's say that's multivariate normal. And I've got some means attached to this. I'll call it mu1 and mu2. This is the same dimension of that, that's the same dimension of that. And I've got some covariances attached to everything. Sigma 1, 1, sigma 1, 2. I'll say this is sigma 2, 1. You know what sigma 1, 2 transposed. So they're not exactly the same things, but they're pretty close to each other. And this is sigma 2. So I didn't say this. This thing, whatever its dimensionality, that's the square of that. Whatever the dimensionality is that's the square dimension here. And these are the things that make this a full square matrix. So that's that dimensionality. If I wanted Z1 on Z2, I could work out this thing from scratch. What you might do is you might take the joint distribution, or I can write out the full joint distribution and then divide by the marginal distribution. Then I would look for the -2 linear terms in all of that, and that would tell me or I would look at the quadratic term, that would tell me something about the variance, and then I'd look at the -2 linear term, that would tell me what the mean is. And so some people are really fast at doing this. If you want to get really, really quick at doing it, take my base class in the fall and we're going to do it over and over and over again. So that'll almost be the entirety of midterm 1 is just doing that exercise over and over and over again. So you can take those densities and work out everything. Let me just tell you what these forms are. So this is some normal distribution and it's got some expectation. So that expectation is just the expectation of Z1 given Z2. I'll write it out like that. Somebody help me out. What is this? There's two terms. There's a plus sign in the middle. What's the first term? mu1. Somebody except for Saeed, tell me what this term is right here. Could you do it?
Something with mu2 and sigma 2.
Go do it.
I don't know what it is.
For real?
I can go right, I think.
Okay, you can derive it. Can anybody write this down off the top of their head for a full epsilon? Okay, let me write this down just real quickly. This is sigma 1, 2. So times sigma 2, 2 inverse, that's that, times, what is this times by? No, you're thinking of the variance.
Correlation.
Wow.
Something with
C2, whatever that is, minus mu2. You know what I call this? Right here. I call that regression. This is your whole regression class with normality in mind. It's that. That is the regression line when you're doing this sort of conditional sort of thing. So if I imagine everything in a joint space, the y's and x's in a joint space, and I ended up trying to come up with the expectation of y given x, that's the regression line, and that's what you get. This is your intercept. This is your slope right here. I guess the intercept is involved with that as well. So, but this is your slope on everything. Remember that. Go put that on a flashcard. Keep that in your brain. You will use this over and over and over again. And I can imagine a situation where you're taking a midterm and either this is a half-hour problem or a 30-second problem. So keep this in mind. So notice. I feel so impressed by this right here, knowing this. And the reason why is I watched somebody do this when I was a first-year student in grad school, and they're just like, tick, 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 tick. And it's like, wow, I got the answer. They just know that off the top of their head. So I went back and I derived this using densities, and it took me a long time to do. And then I was like, geez, I don't want to do that every single time. So this conditional thing comes up regularly. I call this regression. So this really is a different way of looking at regression, and maybe we should kick off our regression classes teaching this first. So this is just a basic property of multivariate normals. The variance of Z1 given Z2, this is equal to sigma 1, 1. That part's easy to think about. Minus sigma 1, 2, sigma 2, 2 inverse, and sigma 2, 1. So that was the part that Chris was thinking about, but he was thinking about the variance. One cool thing to notice is this part right here is a negative sign, which is kind of super cool because it tells us that we're learning. So if there is correlation in all of that, that's measured through this part right here between the two variables. It's also measured through that. If that's a 0, this whole thing is a 0, and we haven't learned anything. But if there is correlation between things, this term is positive and we're subtracting something off, so we're reducing the variability, and that means we're learning.
Is that like why sometimes people induce correlation?
Yes, absolutely, absolutely. So that's like one of my greatest tricks. It's not mine, is model the relationship between things. So build better models that measure the relationship between things, and you'll reduce variability. You'll learn more. So you'll get more power out of your estimates. We'll talk about that in chapter 8. Yeah, absolutely. So that's one. That's one reason, at least the normal vantage point on this. Let's just look at how the Rao Blackwell estimator works here. So for our example that we're working on, we just need the expectation of x1 given x bar. So let's just do the same thing, x1, x bar. I've been getting people on this exam question for like a decade. It's just working this thing out, show the Rao Blackwell estimator, and we can turn it into this very difficult problem. Lots of math, 3 pages, and it really could just be this formula. So if I want this, I want to write this thing down first. X1's mean is mu, so I don't even need an index there. X bar, its mean is mu as well. That's cool, same mu's. And then I come up with the covariance estimates. X1 has variance sigma squared. We know what the variance for x bar is, sigma squared over n. What's this?
0.
It's not 0. X bar has x1 sitting inside of it. So they obviously are related to each other. For 2 full sigmas, there's full epsilons. Not giving away sigmas, we're giving away epsilons.
Sigma squared over n squared.
Sigma,
Should be negative.
no.
No. I'm just thinking it's regression.
One goes up, the other one goes up. X1 is related to X1 positively. Sigma squared over n. covariance x1 with x1 plus xn over n is equal to the covariance of x1 over n. So I just break this up into a bunch of fractions, and this gets summed into k is equal to 2 up to n, the covariance of x1 with xk over n. These are all zeros. Oh, I could factorize out that n, but this whole thing is 0, so I can pull that n out here. These are all zeros right here, and I can pull that n out here. And this is sigma squared. So Colby's error was thinking there was another n under there. So we pulled that thing out with it, but it's just one n, so very, very close. Almost epsilon. So I'll give you a half epsilon for that. So that's what that is. If you plug everything into this formula at the end of the day, you're going to wind up with expectation of x1, so this is going to be mu. So that's that part, plus I've got this thing, sigma squared over n. I'm going to invert that one. Sigma squared over n inverse. This is going to be x2, x bar minus mu. Subtract off its mean. So that's the same formula. It's a funny way of writing 1. The mu's cancel. This is x bar. Boom. So pretty quick. So again, just having these things just in your back pocket, pulling them out, is probably the thing that makes people, either like exams because they know all the tricks or something like that. How do you figure them out? I don't know, do the problem the hard way first, and then convince yourself it's worth remembering not to do that. So I don't have a better exercise than that. Let's prove this statement. So we want to prove that the bias level is exactly the same. We can see that in our example. X bar still has the same bias level as mu, bless you. And the variance of x bar is sigma squared over n, so the variance reduced. That's really sweet. So again, what it tells me is make sure you're using sufficient statistics. I'll also mention once you've iterated through Rao Blackwellization once, you can't keep doing it and keep driving down the variance. You're going to keep getting the equal sign back for fairly obvious reasons. Here's a proof. So expectation of VT, our Rao Blackwellized estimator, I'll just write that out. This is the expectation of W given T, so that's the definition of VT. I'm taking the expectation over that thing, and we know what that is. That's the expectation of W, because this is just the iterated form. It didn't matter what I conditioned on here. This could be any random variable. Didn't have to be the sufficient statistic, just as long as it's some random variable. Because of iterated expectation, we get back the exact same answer. So this thing was cal theta. Not approximately, exactly cal theta. So same bias level. So other part of the proof, I'll do a little bit backwards. I'll just tell you what the variance of W is. So that's the expectation of the variance of WT, W given T, plus the variance of the expectation of W given T. So this is the variance of my Rao Blackwellized estimator. So this is the variance of VT. That's what that thing is. And this thing right here is positive. How do we know it's positive? Variances are positive, expectations of positive things are positive. So this is going to be greater than the variance of VT. So that's just that part right here. And then I'm adding something positive to it, so this thing must be greater or equal to that. And so this variance is decreased from that, which is not stupid. So this is just a recycling of the iterated forms. That's the whole proof. So let me just ask a question. Why did T need to be sufficient? This could be a very good quiz question. For 3 epsilons.
The estimator must only depend on the data.
Yeah, that's right. So if you don't condition on a sufficient statistic, this could be a function of mu. So is what could happen. In our example, this could be a function of theta. So if we ended up working this out in our example, we're going to get something back that I would consider an atrocity if you use this for estimation. Let's do a slightly different example and condition on something that's not sufficient. So x2, for example. I'll just condition on that. So not sufficient. So our proof didn't require a sufficient statistic to show that we've driven down variance. We've conditioned on something. So of course it's going to drive down variance. What happens when you condition on something that's not a sufficient statistic? We get back our exact same formula. So this is going to be mu plus, if you would like to do the thing, this is x1 and x2. This is multivariate normal, mu and mu. They're all scalars, so it doesn't really matter. And then I've got my covariance matrix. So this is sigma squared, 0 and 0. So I didn't learn anything. So there's no learning going on. So this is going to be plus 0. So I'll just do that. You can pre-multiply sigma squared by 0 and subtract and put in that linear term if you'd like, but once I multiply by 0, it's still 0. So you get that back. So that's a great answer. So what should I estimate with? Mu? Mu. I would agree. If you knew mu, you don't need this class. So if you know the parameters somehow, you don't need stats. You're better off. Just take that. Drop out of school right now if you know all the things. So shouldn't be that. If you do know all the things, tell me how you know. I would like to know the trick. I have to use data. Okay, so that's Rao Blackwellization. I might ask about that in the future, but it's just one more reason that we want sufficient statistics. Any questions about that? I'm just gonna set up what we're gonna look at next time. I want to jump into Bayes' risk and circle back to that. There's a couple things I haven't told you about, so I'd like to tell you about them next time, and I would like to give you some theorems. And then maybe we could draw some pictures to prove those theorems, and you could figure out what the right way to tighten that up and write down very formally what the pictures say. So I'll give you some theorems about different types of estimators, including Bayes estimators. But recall, the Bayes estimator is e pi, I'll make this a function of x. This is just going to denote that this depends on prior. So this is just going to be the integral of the risk function. So that's risk. And then I'm going to weight different areas of theta depending on how I like those thetas, how often I think those thetas are important in the risk function. So I have the ability to downplay or upplay different regions of theta. So risk is just a measure of how risky we are at estimating a parameter theta using some set of data on average. So it's an average statement. So this is our prior. They're really just weights. This is just a weighted average, so Bayesians are averages. So there's lots of good reasons to average over things. So I'll rewrite this again. This is just the integral of the integral. So risk is defined in terms of an integral. It uses the loss function. And the loss function is going to compare the truth to the estimator. So an example of this might be the squared error norm, the difference of these two things squared out. It could be the absolute value. It could be the 0-1 loss, things like that. There are other loss functions out there, so but those are the common ones. So times f of x given theta dx times pi theta d theta. And then we're going to R minimize over E. I didn't write that in. So this is the base risk, the integrated risk. If you like to think about it that way. So base risk or the integrated risk. I grew up in an era just saying the word would incite people. Nowadays, we think if you didn't say the word, it can't be that cool. So you say the word, now I'm interested. Okay, you're doing something more modern. So times change. So this is just the risk right here. So this is the average performance of the loss. So it's the expected loss. That's risk or the expected loss. I made a statement that I said there's another way you can think about this. It's the posterior expected loss. So I want to just go through those details one more time and show you don't have to solve this double integral. There's only just one integral after I do some adjustments to all of this that we need to optimize over. And I want to give you some example and show you how easy it is to use this thing. So we're going to circle back to this, and then I want to tell you some theorems about why we like these estimators and what they might guarantee. So there's also other types of estimators out there, the minimax risk. So that's the estimator that minimizes the maximal risk. So it looks over the collection of risk functions of all estimators in the entire universe, and it looks at all their maximal risks, and it throws away all the rest of the risk curve, and it just orders those maximal risks, and it takes the estimator with the minimal maximal risk. And in some cases, I would consider that a good idea. In some cases, I would think averaging over your risk is also a good idea. So it depends on the situation. So if I were trying to predict basketball games against my friends, and I was going to watch a dozen of them or something like that, 32 of them in a weekend, so that's possible, I guess. So, I don't know, I probably watched a dozen in a weekend a couple weeks ago. On average, I want to be right about things. I'll feel really good, and I get the opportunity to repeat my performance. And so maybe being a Bayesian and averaging over the risk is a good idea if I want to beat people. I just don't care how I beat them, just as long as I do well on average, that might be a good principle to use. And so eventually I should do pretty good. If I were building a nuclear facility, I probably don't want to say on average these nuclear facilities seem to be working pretty well. I probably want to look at the most extreme risky event and minimize that thing. And I want the nuclear plants that minimize that. So I don't want to be good on average. I want to be absolutely sure that the maximal damage that can occur is minimized. So I think that makes sense. So again, which criterions do we use? Which estimators do we use? It depends on the situation. So we're going to come back next time and I'll say a few facts about minimax estimators and base estimators. And then, hopefully on Friday, we'll jump into a soft version of decision theory. I'll introduce you to the likelihood ratio, and then I'll tell you what native Pearsonians do. And I'll tell you why they had to fight with